Hello everyone, this is Professor DePaulo welcoming you back to Psych 220 Behavioral Statistics fully online. And this week we're going to be talking about the analysis of variance, which is a logical extension from the two-group t-test. The analysis of variance covers the situation when you have more than two groups and you want to ask if they're different or all the same. So in this chapter, we're going to talk about the analysis of variance, why it's important to conduct analysis of variance, especially versus many different t-tests. It's a much simpler approach to conduct one analysis of variance instead of multiple tests. We'll be focusing mostly on the single factor study, which means you have one variable that has three or more groups or conditions. And then in future chapters, we'll be talking about the factorial design where you have multiple factors. We'll also be talking about when it is appropriate to use post hoc tests and what type of post hoc test to use. More specifically, talking about the difference between Tukey's honestly significant difference test and the Chaffee test. And I personally prefer the Tukey's honestly significant difference test because it's not as conservative as the Chaffee test. The Chaffee test is very difficult to find significant differences when you use it. And then finally, we're going to be talking about effect size and the computation of eta squared, which is that little, that Greek letter looks like an N squared. Eta squared is the effect size measure, and it's interpreted the same way that we interpret R squared, which is the proportion of variance in the data set that's accounted for by the treatment, by the independent variable. So we'll be talking about all these things, setting up the stage for the factorial design to occur later on in the course. So the analysis of variance is a logical extension of the t-test. The t-test compares two conditions or two groups. The analysis of variance compares more than two groups. And that's basically it. If you have two groups, you could run the analysis of variance and you'll get the same answer basically as you get with a t-test. But it's technically preferable to run the t-test for two groups. And then if you have more than two conditions, you're going to run the analysis of variance, and we abbreviate it sometimes as ANOVA. So you hear the word ANOVA. ANOVA means analysis of variance. And we're looking obviously between mean differences between three or more treatments, or three or more conditions, because they don't all have to be treatments. One could be like a control condition. So you have three or more conditions or groups, whatever you want to call it, and you want to see, is there a difference in the mean of these three conditions, 3+ conditions, because you can have many more than three. And so you gather basically three samples, each representing one of the conditions. So if I have three conditions, I have three samples, and I'm using those samples to estimate the population means. So we're really testing to see if the population means are the same or the population means are not the same of three or more groups. We like to use the word factor to represent an independent variable, but you can also refer to a traditional independent variable that's randomly assigned and differentiate that with the quasi-independent variable. These are independent variables that are not randomly assigned. For example, a quasi-independent variable could be gender, could be religion, socioeconomic status, ethnicity. These are all quasi-independent because I cannot control them. As an experimenter, I have no control over these things. They're just naturally occurring. Versus a randomly assigned independent variable where I can manipulate it. So I can assign certain people to get a treatment or a different dosage of a treatment, right? I have control over that. So if you have control over it, it's a true independent variable that's randomly assigned. And if you have a quasi-independent variable, it's basically a naturally occurring group. You're treating them the same way in the ANOVA. So it doesn't matter which of the, if it's naturally occurring or if it's randomly assigned, it doesn't matter. They're treated the exact same way with the ANOVA. The levels are the number of conditions that make up a factor or a variable. So whatever your variable is that you're, if it's gender, if it's ethnicity, if it's religion, if it's dosage of a particular drug that you're taking, those are your factors. The levels are how many different variations are there. So for instance, if you're looking at, let's say, ethnicity, you're going to have many levels. You can have white, Hispanic, African American, Asian, and then you can have like an other category. You can have a variety of different levels of that variable. So you're going to have probably 5 or 6 levels of the variable ethnicity. If you're talking about dosage of a drug, you can get the placebo, which is basically nothing. You can have 5 milligrams, 10 milligrams, 50 milligrams, 100 milligrams. Depends on what you want to look at. But each of those is a level of that factor. Factor is independent variable, and level is how many conditions of that independent variable that you have. Those are your levels. And then the factorial design, which we're not going to look at in this chapter, but we're going to look at later on, is when you have 2 or more factors or 2 or more independent variables. And then you have what are called interaction effects and main effects, and it gets a lot more complicated. For this chapter, we're going to be staying with the single factor design. So you only have one independent variable with 3 plus levels. Now the null hypothesis for the ANOVA is that the means of the multiple levels of the dependent variable, of the independent variable, I should say, the means of those levels are going to be the same. So if I have 3 groups, then the mean of group 1 is equal to the mean of group 2 is equal to the mean of group 3. There's no difference. This is another thing with the null hypothesis, always no difference. So here there's no difference between the conditions, the levels of the independent variable. There's no difference between level 1, level 2, level 3 here. Or if you want to call them groups or you want to call them conditions, it doesn't matter, they're all the same thing. There's no difference between these levels, conditions, groups. If you have more than 3, the null hypothesis is going to say there's no difference between 4 or 5 or 6 or how many levels you have, there's going to be no difference. They're all the same. For the alternative hypothesis, you want to say that they're not all the same. All the levels are not all the same. Now that you're not specifying which ones are different from each other, right? That doesn't mean they're all different from each other. When I say they're not all the same, and that's going to be the alternative hypothesis, that means that basically maybe multiple groups are different. Maybe one group is different from all the other groups. We don't know yet. We're just saying that basically they're not all the same. So the null is all the groups are the same. All the means are the same, the means of the groups. And the alternative is the means of the groups are not all the same. The alternative does not specify where the difference is. It does not specify which groups are different from which other groups. All it says is they're not all the same. So you might think, well, that's not that useful. Well, it's useful in a way, but then there's more additional tests we can do. So if we reject the null hypothesis and we say all these groups are not the same, then we can follow it up and we can actually look for which groups are different from which other groups. And we're going to be talking about that when we get to post-hoc tests. But the overall basic picture of ANOVA is the null hypothesis says all the means are the same, all the groups are the same. The alternative is that they're all not the same. They're not all the same, so we don't know which ones are different from each other. We just know that they're not all the same. So then the question is, why use ANOVA at all? Because ANOVA is just telling us whether all the groups are the same or all the groups are not the same. That's not telling us much information. Well, that's true to a degree. ANOVA allows us to cut down on the number of tests that we run. So for instance, let's say we have three groups. We have three groups or three conditions. And we want to see which groups are basically different from which other groups. I could run with three groups, I could run three t-tests and compare all the groups that way with three t-tests. Or I could run one ANOVA. Now, why not run three t-tests? The reason to not run three t-tests is every time that you run a hypothesis test, there's always a chance you're making a mistake. There's always a chance of type 1 error when you reject the null hypothesis incorrectly. That means the null is true when you reject it in your sample and you've made a mistake. And we generally set that type 1 error or the alpha value at 0.05. So we're basically saying there's a 5% chance every time we test a hypothesis that we can make a mistake. Well, if I test one hypothesis, the total error rate is 5%. But if I test two or three, the error rate goes up and up and up. So the more tests that I run, the higher the probability that I'm going to make a mistake. That I'm going to reject the null when the null is true. I'm going to make an error rejecting the null. So that's why you don't want to run that many tests, because you could make a type 1 error. And that's technically called the family-wise error rate. It's basically, if you run all these tests in your study, what percentage of chance is it that you're going to make one or more type 1 errors? And the more tests you run, the higher that family-wise error rate goes up. And as a researcher, that's not good, because if I'm running a bunch of tests, I might reject one null hypothesis just by making a mistake, by a type 1 error, because I ran so many tests. So the ANOVA cuts down on the number of tests that you run. In that way, it lowers the family-wise error rate. It makes it less likely that you're going to commit a type 1 error. And that's important. Once you reject the null with the ANOVA, then you can follow up on it by running what are called post-hoc tests. And the difference with the post-hoc tests is the post-hoc tests keep your error rate lower than if you were just running a series of t-tests. Now you may say with three groups, it's not that big of a deal to run three t-tests. And I might agree with you. Three groups, three t-tests doesn't sound much different than running one ANOVA. But what if you have four groups? Now you have 6 t-tests you'd have to run. That's a lot more than running one ANOVA, and the error rate can go up. What if you have 5 groups? Now you have 10 t-tests you would have to run to compare all those means. So now you're in a condition where you have 5, if you have 5 conditions or 5 groups, you're at 10 t-tests, and the alpha rate is at 0.05, and it's going to be compounded. And we can calculate the actual probability of making a type 1 error if I wanted to do that, but I don't have to do that now. All I can say is if you're running 10 t-tests, your error rate is going to go up. So why run 10 t-tests when I can run one ANOVA? And guess what? It saves me time. I run one ANOVA, and if I fail to reject the null with the ANOVA, I don't have to run any more tests. Whereas if I did the 10 t-tests, I would have to run 10 t-tests under every condition. So not only does it cut down on your error rate, it cuts down on the time spent running the tests, and it's just overall a better idea to run the ANOVA than to run a whole bunch of separate t-tests. So once I am planning to run the ANOVA, I have to be able to evaluate the results of my ANOVA. And the ANOVA goes by something called the F ratio. The F ratio is based on variances instead of sample mean differences. And the reason why is, let's say I have 4 conditions. How do I determine the mean difference when I have 4 means? If I'm going to say all the means are the same, how do I compare those means? There's four means. Do I subtract them all from each other? Do I add them together? It doesn't make any sense with four means. I can't determine whether those means are all the same in a very simple manner. With a t-test, you have two groups, so you could just subtract one mean from the other. That makes sense. With four groups, five groups, six groups, how am I going to do that? I can't. So instead, what we're going to do is we're going to compare variances between those sample means. So those sample means are associated with variances, and it's much easier to calculate the difference in the variances between the means than actually calculating the difference in the means in any way that makes any sense to calculate, right? So we know that if there's a big difference between means, then the variance is going to be bigger. If there's a small difference between means, then the variability is going to be smaller. And that's the numerator of this F ratio. Now the F ratio is similar to the F ratio we calculated, the F max ratio we calculated before in one of the previous chapters, where an F ratio is a ratio of two variances. In the case of ANOVA, the numerator is the variance between the sample means. And if the means are spread out more, if the means are further apart, then the variance between those means is going to be bigger, right? So whenever those means are apart, further apart, the variability among those means is going to be greater than if the means are close together. So that numerator is basically the variability between the means. The denominator is the variability if the null hypothesis is true. Now, when the null hypothesis is true, the means are all the same. So the variability is just the variation within each of the treatment conditions. So think of the numerator of the F ratio as the variability between the means, which is basically the treatment effect. So how well is the treatment working? If the treatment is working well, there should be more variation between the means. And the denominator is sometimes called the error term or the within groups variance. And this is individual differences. So if everybody gets the placebo and I monitor their depression levels and I'm trying to treat them for depression with a placebo, some people in that group that get the placebo are going to say, yeah, I feel a lot better. I'm less depressed. Other people are going to say, I'm very depressed. So in some people that get the placebo, they're going to actually do better than other people that get the placebo. Why is that the case? Well, because people are different. These individual differences are what are called the within variance estimate. So individual differences within each condition is going to be in the denominator of this F ratio. Because if there's no treatment effect, that means if the null hypothesis is true, then the only variability is going to be within each of those groups. So the group that gets a placebo is going to have some variability. The group that gets 10 milligrams of the antidepressant is going to have some variability. The group that gets 20 milligrams is going to have some variability, etc. Not everybody that gets the same treatment is going to react the same way. So that is called the individual differences, right? But technically in statistics, it's called the within groups variance or within groups variability, or sometimes called the error term. Error means random. So anything that's not due to the treatment is random. In statistics, it's called sampling error, right? It's random variability. Not everybody that gets a particular treatment is going to react the same way because people are different. Animals are different. There's always going to be some random variability. And that's what we call the error term or the within groups variance. That's on the bottom. So the top is variability caused by the treatment, and that's in the numerator. The denominator is variability not caused by the treatment. That's caused by individual differences, basically. So as I mentioned, we can't compare the means directly when we have more than two means. So we're looking at the variances, and it makes sense. that if the means are further apart, then the numerator of the F ratio is going to be bigger. When the means are closer together, then the numerator of the F ratio, that variability, is going to be smaller. And that's basically how we're kind of inferring the the uh, the impact or the difference between the means. We're inferring that difference by looking at the size of the variance between the means. So the between variance estimate, between treatments variance, is the numerator of the F ratio, and that's due to the treatment. The within groups variance, as I mentioned previously, is the denominator, and that's due to individual differences. So I'm repeating myself a little bit because I want to kind of hammer this point home. Numerator of the F ratio is between treatments variance, and that's due to the treatment, the effect of the treatment. The denominator variance estimate is called the within treatments variance, and that's due to individual differences within each condition. So numerator is systematic differences caused by treatments. Denominator is random error, individual differences, measurement error. And then we put it together. And we add the F ratio. Differences including any treatments effects on the top. The denominator is differences with no treatment effects. Now, as a researcher, I want this F value to be as big as possible, because what that means is that there are huge differences with the treatments, right? And I want there to be a big difference with the treatments, and I want there to be smaller individual differences. That's the denominator. That's my goal. But the bigger the treatment effect, the bigger the numerator, and therefore the bigger the F ratio. Now we can partition the total variability in your sample into two components: the between treatments variance, which is the treatment, but it also occurs some random unsystematic factors. So there's always an element of chance when people, whatever they respond on the variable, there's always some chance involved. But the between treatments variance is mainly the effect of the treatment. Within treatments variance is just chance, random error. And we can break up the variability this way, and that's what we're going to do when we calculate the F ratio. We're going to break up the variability for the treatment, and we're going to break up the variability for the error term, or the within groups variance. So if the null hypothesis is true, the size of the treatment effect is going to be near 0, and the F ratio is going to be near 1. So basically, if the null is true, then the treatment doesn't have any effect. So the treatment effect is basically 0. And then what you have in the F ratio is you're going to have random error on the numerator divided by random error in the denominator. It's going to be 1. So an F value close to 1 is when there's no effect. That means the null is basically true. An F value much greater than 1 means that the null hypothesis should be rejected. Now, the F statistic is different than T because the F statistic does not have negative values, because this is a ratio of variances. Variance, by definition, is a squared term. So you have a squared term divided by a squared term. Squared terms are non-negative, right? So you're going to have a non-negative number divided by a non-negative number, and you're going to have basically, a positive number. You're not going to really have 0. Almost, I can't even imagine having 0 as an F value. You're going to have something, if your null hypothesis is true, you're going to have something close to 1. It's going to be a positive value. There's not going to be any negative values. So it's a lot different than the t-test where you have a positive tail and a negative tail. The F distribution only has a positive tail. It's a skewed distribution. It's positively skewed. So let's check some things fast here, see what's going on. The first statement is that ANOVA, analysis of variance, allows researchers to compare several treatment conditions without conducting several hypothesis tests. That seems reasonable. This is kind of what I was talking about. Um, you run one ANOVA versus multiple t-tests. The second statement, if the null hypothesis is true, the F ratio should be 0. Obviously, it's a ratio of two values, and error on the top divided by error on the bottom is not going to be 0. So the answer is true, that ANOVA simplifies things so you can conduct one test instead of several t-tests, and obviously false. If the null hypothesis is supported, the F ratio will be near 1. You're not going to see an F ratio near 0. The F ratio is almost always close to 1 if the null hypothesis is true. Now here are some of the notations for the rest of this chapter. The number of treatment conditions is called K. K is the number of conditions. The number of scores in each treatment. If it's in each treatment, you get a little n. So little n sub 1 means the number of people in condition 1, or number of data points in condition 1. Little n sub 2 means the number of people or data points in condition 2. The total number of people or data points in the whole sample, regardless of condition, is called capital N. So it's important to differentiate capital N, which is the total number of subjects, compared to the small n, which is the subjects in each condition. The sum of scores, the sum of x's for each treatment, is represented by capital T. The grand total, the sum of all scores in the entire sample across all treatments, is capital G. Capital G stands for grand total. And it's the sum of all the treatment sums, right? So it's the sum of T. T is the sum in each condition for each treatment, and G is basically everything added together, all the treatments added together. Now this is just one way of doing notation. Other textbooks will use different symbols. So you'll come across all different symbols depending on the textbook or depending on whatever online site you're looking at. Everybody uses different notation. This is pretty basic notation, so I don't think it's that difficult to understand. You just have to get used to K, N, T, and G. And once you know those, you're pretty much okay. And little n as well. So if the F ratio is the variance between treatments, the treatment effect divided by the variance within treatments, which is also known as the error, you can break this up. The variance between treatments is the sum of squares between divided by the degrees of freedom between. So you remember how we calculate variance. It's sum of squares divided by n minus 1. N minus 1 is the degrees of freedom. So you're doing that for between, the sum of squares between the treatments. That's basically the sum of the square deviations between the means of each treatment. Divided by the degrees of freedom between, and we'll talk about that shortly. And the variance within, the denominator, is going to be the sum of squares within, which is basically each score minus the mean of that group, finding the sum of squares that way, divided by the degrees of freedom within. So the sum of squares total is always the sum of the sum of squares between plus the sum of squares within. And the degrees of freedom total is always the sum of the degrees of freedom between plus the degrees of freedom within. So this is partitioning. We're partitioning the variance. And then we're partitioning the degrees of freedom. So to find the sum of squares total, we take the sum of x squared, which is the sum of all the squared scores. So the first thing you would do is square every score in your sample, square the whole thing, regardless of condition. Square all the scores, add them all up. That's going to give you the sum of x squared. And then subtract g, the grand total, which is the sum of all the scores, regardless of condition. So add up all the scores, then square that sum, and that gives you g squared, and then divide that by the total sample size across all conditions, which is capital N. That can then be partitioned into between and within. So between, the sum of squares between is found by taking the sum of t squared. T is the sum of the scores in each treatment. So if you have 3 treatments, you're going to have 3 t's. You're going to have T1, T2, T3. So then you would basically add up all the scores in each treatment condition and then square those sums, and then divide those squared sums, the t squared, divide that by the sample size in each condition. So the small n represents the sample size in each condition. So once you've done that, then subtract g, once again the grand total, the sum of all scores, squared divided by capital N, which is the total sample size. That will give you the sum of squares between. Then if you want to find the sum of squares within, you just have to basically find the sum of squares each of the conditions and add them together. So if you had 3 groups, you'd find the sum of squares for group 1, the sum of squares for group 2, and the sum of squares for group 3, and you add them all together. And that would give you the sum of squares within. So that's what you've been doing previously in the previous chapters. You've been finding sum of squares just with a group of scores. You're going to do that here, but you're going to add up, you're going to do that within each of the treatment conditions, so each level of the independent variable, and then you're going to add up those sum of squares. And when you put it together, you're going to have sum of squares total. So basically, when you add the sum of squares between and you add the sum of squares within, you're going to get the sum of squares total. And here are the equations written out. As I mentioned before, sum of squares total is the sum of all the squared scores minus the grand total, which is G, capital G, which is the sum of all the scores not squared, right? Square that grand total, divide by capital N, the total sample size. The sum of squares within is just find the sum of squares in each of the conditions and add them together. And then the total, or actually you can find the sum of squares between by doing the sum of T. T is the sum of the scores in each treatment condition. So square those sums of the scores, those T values, divide by the sample size for each condition, which is lowercase n, and then subtract the grand total of scores squared divided by the total sample size, which is capital N. And you have to kind of practice this. So if you go online in the chapter, there'll be a bunch of sample problems, and you want to go through them step by step and just practice. You know, those example problems where you can just basically run them over and over again. You keep doing them forever. But basically understand the notation and be able to do them, you know, reliably. So when the exam comes, you know what all these things are. You're not lost. And the calculation is not hard. This way, you're going to have all whole numbers, so you're not going to have decimal points this way, as opposed to doing it where you basically, you could do this another way where you find the grand mean, which is the mean of all the means, and then subtract each individual mean, subtract that minus the grand mean and square it, and then weight it, multiply it by its sample size. You could do it that way, but that's going to be a lot harder, and the book doesn't even talk about this. But that's another way you can calculate it. It's not mentioned in the text because it's a hell of a lot longer and harder way of calculating the ANOVA. It just doesn't make any sense. But I mean, I've done it that way too. It's the conceptual method. This is the computational formula. It's much easier doing it this way. So I suggest you just practice it with these equations until you feel comfortable doing it this way. And it avoids all the decimal points and squaring the decimal points. And it's just a mess doing it the other way. So this is a pretty basic way of doing it. Not necessarily easy. It's not necessarily hard either. It just requires you to practice. So that's what I'd expect you to do. So go on to the online on the site and go to those, watch the walkthrough videos that are posted, and then actually do the practice computation where they have the option of doing that, and just keep doing it basically until you feel comfortable. Don't just like rely on this and say, okay, I understand it, and I don't have to do any of the problems, because it's gonna be very confusing. So you want to actually practice some real problems with these formulas. Now, the degrees of freedom are calculated in the following way. The degrees of freedom total is n minus 1. The degrees of freedom within groups is n minus k, where k is the number of conditions. So if you have 3 conditions, k is 3. If you have 5 conditions, k is 5. And then between groups, degrees of freedom is k minus 1, the number of conditions minus 1. And the degrees of freedom within plus the degrees of freedom between must equal the degrees of freedom total. They add together. And that's what you have here. Degrees of freedom total, n minus 1. Degrees of freedom between is k minus 1. K is the number of conditions or number of groups. And degrees of freedom within is n minus k, where k is the number of groups or conditions. So this is fairly basic. But you need to have both the sum of squares broken down to total between and within. You need to have degrees of freedom broken down to total between and within. Now, once you've done that, we can calculate something called the mean squares, and then the F ratio. The mean squares is like the average of the variance. So the mean squared between is equal to the sum of squares between divided by the degrees of freedom between. So that's basically the average variance between groups. It's equal to the sum of squares between divided by the degrees of freedom between. The mean squares within is equal to the sum of squares within divided by the degrees of freedom within. And then the F ratio is simply the mean squares between divided by the mean squares within. So it's a ratio of those two variance estimates. Let's take a look at these learning checks again. An analysis of variance produces a sum of squares total of 80 and a sum of squares within of 30. What is the sum of squares between? Well, that's basic because we know that sum of squares between plus sum of squares within must equal sum of squares total. So what plus 30 gives you 80? And obviously the answer is 50. So the sum of squares between must be 50, and when you add it to the sum of squares within, which is 30, you get the total sum of squares of 80. Now, as previously mentioned, if the null is true, the F ratio will be around 1. The F ratio is always a positive number, cannot be negative. And if you look at the table of F in your text, there are 2 degrees of freedom in the table. You have a degrees of freedom numerator and a degrees of freedom denominator. The degrees of freedom numerator is the between groups degrees of freedom, and that's equal to k minus 1. And that's shown in the columns of the table, degrees of freedom numerator. Degrees of freedom denominator is n minus k, and that's shown in the rows of the table. So what you want to do is you want to find the numerator degrees of freedom between groups, the denominator degrees of freedom, and find the intersection point in the table. And then determine if you need 0.05 or 0.01. So there'll be 2 values. There's going to be a 0.05, which is the plain-faced value, the regular text, and then you'll see a 0.01 critical value. and that's going to be in bold. So depending on if we're using 0.05 or 0.01, that determines whether you use the non-bold or the bold number as the critical value of f. And once again, we want our obtained value of f to be greater than the critical value of f. There's no two-tailed test. There's none of that here. There's only one tail of the f distribution. It's positively skewed. There's only one tail. So all we have to do is see is our obtained value of f that we computed, is it greater than the critical value of f? If the obtained value is greater than the critical value, we reject the null. If the obtained value is less than the critical value, then you fail to reject the null. Simple as that. You don't have to worry about directional, non-directional, one tail, two tail. It's just basically one tail here. And here's your one tail. This is what f looks like. You see that if you see by 1, you see most of the scores in the f distribution are near 1, the ratio of 1. And that's because, on average, your f value is going to be close to 1, which means that the null is not true. The null is true, I should say. You want your values to be in the tail of the distribution. The further in the tail, the better. If you look at the 5% value, now the degrees of freedom will change the exact values, but you see that the 5% value, the F ratio, is much lower than the 1%. So it's really hard to reject the null at 1%. If you want to set your alpha value at 0.01, it's going to take a very big F ratio. But at 0.05, it's going to take a moderate size F ratio. But you're only having one tail because it's positively skewed. There's no two tails here. So we do the hypothesis testing the same way we've done T, except that we have only one tail, so we don't have to worry about directional versus non-directional. You're going to compute the sum of squares total, the sum of squares between, the sum of squares within, and then compute the degrees of freedom as well. And once you've done that, you're going to compute the mean squares total, the mean squares between, the mean squares within, and then using the between and within here, you're going to compute the F ratio. And once you've done that, you can make one of these nice ANOVA summary tables. And this is a very good way of presenting the results of the ANOVA. It's not shown really in publications just because there's not enough room for this. But to organize to sort of identify what's going on, especially at the beginning when you're first learning this, an ANOVA summary table is useful. So here you have sources, you have between treatments, you have within treatments, and you have total. And then you have sum of squares, degrees of freedom, mean squares, and F. So you see the sum of squares add together to get 60. The degrees of freedom add together to get 12. And then the mean squares are the F ratio. So 20 divided by 2 gives you 10 as your F value. And that's a pretty decent F value. That's going to pretty much reject the null almost always. Now, once you've computed ANOVA, you can then measure the effect size. So what is the true effect of the independent variable regardless of the sample size? That's the effect size. It is called eta squared. It's similar to R squared, which we're going to be talking more and more about when we get to correlation. R squared we used with the t-test for the effect size. It was the proportion of the variance in the dependent variable that was accounted for by the independent variable, by the treatment. And so the same thing with eta squares. It's basically the amount of variation, the amount of total variation that's accounted for by the treatment effect. So we compute it by taking the sum of squares between and dividing it by the sum of squares total. And the larger value, the better, the stronger the treatment effect. If we're writing this up into APA style, you're going to put the F, you're going to indicate that you did an F test, which is ANOVA, So capital F, in parentheses, you're going to put the degrees of freedom between, comma, the degrees of freedom within. So in parentheses, you have degrees of freedom between, comma, degrees of freedom within. And then equals your actual F value, comma, the significance level. So is it less than 0.01 or is it less than 0.05? Comma, and then the effect size, which is eta squared. And put the eta squared value. And that should be in any kind of APA style write-up if you're trying to publish something. And you'll see this more when you get to research methods. How do you want to represent the results of your research? Now there's a few assumptions that you have to take into account before you run the ANOVA. So the observations must be independent. So if you're running this this one-way ANOVA, right, this one variable ANOVA, you have to have different people in each condition. So they're independent of each other, right? The population from which the samples are selected must be normal, or you have to have a sample size of 30 or more, which basically guarantees normality in each level. So 30 or more in each level of in each condition or level of the independent variable. The populations which the samples are selected must have equal variances. This is the homogeneity of variance assumption. You saw the same thing with the t-test. With the independent groups t-test, you have to have equal variances. The same thing with ANOVA. You have to have equal variances. Now, most of this stuff is very, amenable. It's very flexible. These are not like hard and fast rules. So the fact that you can run ANOVA, even if you don't have perfect agreement with these assumptions, means that the test is what's called robust, especially if you have equal sample sizes. So if you have equal sample sizes in each condition of your ANOVA, your variances could be pretty much way off, and you're still going to get reasonable answer, right? So if you have equal sample sizes, you can violate these principles a bit more. However, the most important one of these three is the homogeneity of variance assumption. If your variances are way different, right? Like let's say you have a variance of 2 in one condition, and then you have a variance of 100 in another condition. Those variances are not even close to being the same. So if your variances are way different, you're going to want to stop using the ANOVA, even with the equal sample sizes. If your variances are way different from each other in each of the conditions, you're not going to want to run ANOVA. You're going to have to run a non-parametric test. There's something called Kruskal-Wallis ANOVA, which is a non-parametric version of ANOVA. It's not ideal because it has lower power, but you could run it. So if your variances are different, what you want to do is test them using the Hartley Fmax statistic that we went over a few chapters ago in the independent groups t-test, the Hartley Fmax test. So you're going to take the largest variance, and then you're going to take the smallest variance, and you're going to compare the ratio of the largest variance and the smallest variance. So it doesn't matter how many groups you have, just take the largest variance and the smallest variance and see how different they are. If the ratio of the largest to the smallest variance is much greater than 4, you're probably going to have problems with the homogeneity of variance assumption. But you can statistically test the Hartley Fmax test, and there's a table that shows you the critical values. But the rule of thumb is that the largest variance should be no more than 4 times the smallest variance. And thankfully, most of the time, this is not an issue, that you have really different variances. But you should look at it before you run the ANOVA, especially if your sample sizes are not equal. Now, once you get a significant ANOVA, all it's telling you is that all the means are not the same. So all the groups are not the same. It does not tell you which groups are different from which other groups. In order to find out which groups or which means are different from which other means, you need to compute post-hoc tests. Post-hoc tests are they're basically t-tests. But the difference between these and regular t-tests is that these post-hoc tests control for the overall error rate in your experiment, the overall type 1 error rate. So it controls what I called before the family-wise error rate, whereas regular t-tests don't. So the chance of making a type 1 error, it can be extremely high if you run many t-tests. If you're running these post-hoc tests, these tests will control or keep under control the level of the type 1 error in your study. Posthoc tests compare two individual means. So it compares a pair of means at a time. So if you have three groups, it's gonna be a posthoc test that'll compare group 1 with group 2, group 1 with group 3, and the group 2 with group 3. So you have three posthoc tests. If you have four conditions, you're going to have six posthoc tests. You're going to have group 1 with group 2, group 1 with group 3, group 1 with group 4, group 2 with group 3, group 2 with group 4, and group 3 with group 4. Those are your six posthoc tests. You want to run all possible comparisons. And with 3 or 4 groups, it's not a lot, but when you're up to 5 groups, you're going to have 10 posthoc tests. If you're up to 6 groups, you're going to have 15. If you're up to 7 groups, you're going to have 21. So it's getting bigger and bigger and bigger, and it gets kind of, you wouldn't want to do this by hand. I mean, the computer will do it for you. But if you want to just learn the idea of posthoc tests, you can compute it by hand. And that's what we do in the classes. We'll be computing these by hand, and maybe computing them on the computer depending on what Excel does. And I'm not sure how much Excel will do in terms of posthoc tests. You would really want to use SPSS or SAS or R, Systat, some of those really popular stat packages. Excel is not that. Excel is kind of convenient, and it's really the only thing we could use during the pandemic, because I'm not going to have you go out and spend money on SPSS. It's too expensive, and Excel is basically free, and it does some things. I'm not sure how much it does in terms of the posthoc test because they never really use it, but we'll be doing some ANOVAs in Excel, and we'll see how much we can get out of that. That'll be later on, a couple of weeks down the line here. So my favorite posthoc test to run is the Tukey Honestly Significance Difference Test, or the Tukey HSD. And this gives me a value that determines, so when I compute this HSD statistic, it gives me a value that allows me to see what the minimum difference between the means, sample means have to be in order for me to say they're significantly different. So if the means differ by anything greater than this HSD value, I could say they're statistically different from each other at whatever your alpha value is. And how do you compute this HSD? HSD is equal to Q. Q is a rather strange stat. Q is called the studentized range statistic, and there's no real reason to sort of go into what it means. But basically, you have to look up Q in the table in your textbook. There'll be a table of Q that you can find. So you need to know what the your K is, the number of conditions. That'll give you your Q value. And then Q is multiplied by whatever that Q is from the table. It's going to be multiplied by the square root of the mean squares within, which is the error term, the denominator of your F ratio. So you have that already. It's the denominator of your F ratio, divided by N, the sample size. One other quirk for the Tukey test is that you have to have an equal number of subjects in each of the conditions. So n is the number of subjects in each condition. It's got to be the same. To run the Tukey HSD, it's got to be the same. If it's not the same, there's an alternative Tukey test to run that we're not going to talk about in this course, but where you kind of weigh by the sample size. But in this situation, the Tukey honesty significance difference test, we're assuming that the sample sizes for each of the conditions is the same, which may or may not be realistic in your study. There's an alternative postdoc test that your book talks about, and there's many different postdoc tests. I mean, if I look at SPSS, there's probably like 15 or 20 of them, and there's no point even talking about them. Tukey is probably the one I use the most. And the reason I use Tukey is not super conservative. So you can find differences with Tukey. It controls the family-wise error rate pretty well, but it's not overly punitive. The Chaffee test, which your book talks about, is overly punitive. It's extremely conservative, which basically means it's going to be very hard to find differences between means using the Chaffee test. It's much easier to find those differences using the Tukey test, which is kind of why I like to use the Tukey test, because I want to actually find differences, because that's what makes my research interesting, is when I can say I supported my hypothesis, right? It doesn't mean that like one is better than the other. It just depends on your point of view. Do you want to be conservative, or, and if you're conservative, you're less likely to make a type 1 error. Or are you going to be more liberal about what's, significantly different, and you're going to say, okay, I may make a type 1 error, but it doesn't concern me as much. So in psychology, I think most people are very liberal with their hypothesis testing, and they do make type 1 errors. And whether that's good or bad is debatable. But if I'm testing for a drug, let's say I'm testing for a vaccine that's going to cure a deadly pandemic, I don't want to be very liberal, because I don't want to make a type 1 error if I'm testing a vaccine that's going to save people's lives. Because if I make a type 1 error and then I scale it up and I distribute it to the whole country, and I made a type 1 error, then it's not going to work. And I've just wasted tons of money, and I've also basically ruined the public's perception of the vaccine, that people will never get the vaccine then. So in that case, if I'm manufacturing a life-saving drug, vaccine, treatment, that has to work, that I can't make a mistake and have it not work, then I'm going to be very conservative. Then I don't want to make a type 1 error. I want to be very, very conservative. But in psychology, you're not facing this kind of choice, right? So if you reject the null and you support your hypothesis, what's going to happen? It's not like, the whole country is going to get sick and die, which is a good or a bad thing. I mean, I think that there's some interesting findings in psychology, because we're not being overly restrictive with the statistical testing, but then there's also this non-replication experience where, one researcher finds a result, and then another researcher tests it and doesn't find the same results, and then they're like, who's right and who's wrong? And the reason it could be is because the first researcher might have made a type 1 error. We don't know. You won't know unless you do it again and again and again, and then see if you can replicate it or not. The Chaffee test is very conservative. So if you had a situation where you wanted to be 100% sure, 100% accurate that there is a difference, you could use the Chaffee test. But there's going to be times where you're not going to find that difference because the test is very conservative. So there's benefits and there's pitfalls for each of these tests. There's no like one best test. Some are more liberal, some are more conservative. Chaffee is very conservative. The Bonferroni correction is ultra conservative, probably the most conservative out of anyone. The Tukey test is it's probably middle of the road. It's a lot more liberal than the Chaffee test. There's this Ryan, Elliott, Gabriel, Walsh statistic that was actually developed by those 5 people that found it, so they named it after them. That's in the statistical software packages you can run. That's pretty fair. Um, you know, I like Tukey though because it's used by a ton of people. So why not use it? It's not, and it's also not conservative. So with the Shafei test, you have to compute an F ratio between the two conditions. Okay. So basically, you have to use the two groups. So if you're comparing two of those groups, let's say you have three conditions, and you're comparing two conditions to see if they're different, you want to use the mean squares between those two conditions and the mean squares within those two conditions. So this part is only calculated with the two conditions, not all the conditions. And then you're going to find the F ratio. And it's going to be hard to find differences using the Shafei test, as I mentioned. So let's check here to see what combination of factors is most likely to produce a large value for the F ratio. Obviously, large mean differences means the numerator is bigger, so that's important. And small sample variances means the denominator is smaller. So if I want a big numerator and a small denominator, I'm going to pick B. And that's the answer. Large mean differences gives you a larger between groups variance estimate, and small sample variances give you a smaller error term. Smaller within groups variance estimate gives you a larger F ratio. True or false? Post-tests are needed if the decision from the analysis of variance is failed to reject the null. So if you fail to reject the null, then all the groups are the same. And if all the groups are the same, you don't need post-hoc tests because all the groups are the same. You're not going to find any differences because all the groups are the same. So if you fail to reject the null for ANOVA, you never do post-hoc tests. So that obviously is false. You don't need post-hoc tests. You only need post-hoc tests if you reject the null. And the report shows ANOVA results of F of 227 equals 5.36, P is less than 0.05. You can conclude that the study had 30 participants. Well, yes, because the degrees of freedom between here is 2. The degrees of freedom within here is 27. So add them together, that gives you 29 total degrees of freedom, right? And total degrees of freedom is n minus 1. So if n minus 1 is 29, then n has to be 30. So that's obviously true. That's exactly what we find here. Post-hoc tests are needed only if you reject the null, right? And degrees of freedom is n minus 1. Degrees of freedom total. Degrees of freedom total equals degrees of freedom between plus degrees of freedom within. Now the last topic is what's the relationship between ANOVA and the t-test? So if you have two groups, you can calculate either t or f. I would prefer to use t because technically if you have two groups you should always use t. But if you use f, you're going to get the same answer, just a different number. So f, when you have two groups, f is equal to t squared. And you always have the same decision whether using t or f. You just have different numbers. So f is equal to t squared. And for any value of alpha, if you take the critical value of t and you square it, you'll get the critical value of f. So if you ever wanted to use ANOVA, now this would have to be obviously with the non-directional hypothesis. You cannot do one-tailed test with f. So this would have to be a two-tailed t-test. Could you use f instead of t for two groups? You could, but why? There's no reason to do that. I would have a problem with that. Now I've seen this in many papers where they do f with two groups and it bothers me because you have t for that situation. So why use ANOVA if you don't have to use it? Doesn't make much sense to me. I'd prefer to use a t because technically it's more correct. When you have two groups, use t. When you have more than two groups, use f. But people do f with two groups as well. and I would advise against it, but f is equal to t squared, so it's technically correct. And this is what it looks like. So you see with, if I did the t-test and I had critical values of 2.01 and negative 2.01, if I take that critical value 2.01 and I square it, I'm going to get the f critical value 4.41. So then I can compare my f to the new critical value, which is 4.41. Why do it? I don't know. I don't see the point of doing it. It's interesting to know that f equals t squared when you have two groups, when you have 1 degree of freedom between. But is it something that that you need to use? No. It's just an interesting mathematical transformation. So that's it for this chapter. There's a lot of information in this chapter. It's a whole different way of thinking because now we've gone beyond the tails and we're dealing with the variance, the ratio of variances, and determining to reject the null based on variances instead of means. So it's a completely different subject here, ANOVA, but it's very important, especially for research in psychology. It's extremely important because most of our experiments are not going to have two groups. We're going to have more than two groups many, many times. And so we need ANOVA. And so practice the problems, do the online practice in the book, the online book, where they have the tutorials where you can go practice, and then just work those problems over and over again and see if you can figure out, the difference between G and T and all those different K. Get familiar with that and work out the problems because there'll be a couple of problems on the final exam, that'll involve ANOVA. And this is the foundation for the next chapter, which is going to be, there's repeated measures and there's factorial. So hopefully that makes sense. A lot of information, so slowly digest it. If you have any questions, email me or make an appointment for my office hours with the link that I've posted on Blackboard already previously. You can always click on that link and make an appointment. But if you make the appointment, please show up for the appointment. Or you can just email me. I'll get back to you usually within a day, unless I'm really, really swamped. So hopefully that makes sense. Hope that helps you in some way. And let me know if you have questions. So bye for now. See you next time.